some terminology and fundamental ideas, concepts in nuclear chemistry. Now we're gonna look at how we can start explaining the stability of the nucleus, or actually the opposite. How can we explain the instability of the nucleus? What we have here is a plot, and as we always do with our plots, we look at the axis first and the units. So we see that the vertical axis corresponds to the number of neutrons and the horizontal to the atomic number. This line here would correspond to the situation in which the number of neutrons and number of an atomic number are the same. Therefore, this line would be a straight line with a slope of 1. The ratio is 1. So the atomic number means that we would be starting with the lightest elements on the left, like hydrogen here, and as we move up, we go to the heavier elements. And we know 118 elements. And this would be, again, the neutrons in the nucleus. So the dots correspond to the known stable isotopes or nuclides. And this plot is given a few different names. One of them is the band of stability, to remind you that this band that you get when you plot all of the stable isotopes corresponds to that. The region in this plot where the isotopes, the nuclides, are stable. So anything that's not on this plot would be unstable, which is one part of the answer to this question we've got here. What can we tell about nuclides that have Z value greater than 83? If they're greater than 83, they would be in this region, and we see there are no stable isotopes. So we don't know of any nuclide with Z greater than 83 that's stable. That's one of the things that we draw from this plot. What else do we see? It says here, let's look at values for Z from 1 to 20. So this region here, 1 to 20, that would be going from the element atomic number 1 to the element atomic number 20. What do we see? What can we say about the ratio? What kind of ratio favors stability? So when we look at it, we see that these dots, these nuclides, are very close to ratio of 1, which corresponds to the line. So we could say that for the lighter elements or nuclides, they tend to be stable when they have about the same number of neutrons as they have protons, when that ratio is 1. We get that from the empirical data, from the plot that comes from observations. So for elements or nuclides that are between 21 and 83, what can we tell? If we look at the elements in this range, we see that the dots are above the line that corresponds to to the ratio equal to 1, equal number of neutrons and protons. So if those points, if those dots are above that line, that means that the stable isotopes or nuclides between 21 and 83 are those that have values for that ratio that are greater than 1. And if you look at a few of them, you can approximate those values. You know, like if you look at Z50 and you go up and see where are the dots that correspond to C50, you see that they're around 70, 75, which means that value is like 1.2, 1.25, 1.3. So that helps us see where the stable isotopes are, and by doing that we can tell where eventually where the non-stable isotopes are, but we can also predict the kind of reactions that unstable isotopes would undergo to become stable. And let me explain that by using this one example here. Let's say that we have this red dot. It's a nuclide. Evidently, it is unstable because it's not on the band of stability. And the question is, when it decomposes to give a more stable nuclide, what happens? Okay? So if it is unstable, it will decompose, it will decay to become more stable, which means it will tend to approximate, to get closer to the band of stability. What needs to happen for that to be the case? We see that that red dot has a ratio that is larger than needed to be stable. So how do we make that ratio smaller? We can diminish the number of neutrons and or increase the number of protons, because the ratio is neutrons over protons. So if it is unstable because the value is too high, we need to make the number of protons smaller, the number of neutrons smaller, and or the number of protons larger. Okay? And I'm going to let you choose which one of these options is correct, or if there's more than one, which of them are correct. We have another example here. This nuclide is unstable too because it's not on the band of stability. But in this case, we see that it has a value for that ratio that is lower. It is lower than ideal. So if the value is too small, what needs to happen to that nuclide to make that ratio go up? Again, since we have that ratio, that is number of neutrons over number of protons, and we need to make it larger to make it more stable, get closer to the band. So we need somehow to have more neutrons and or fewer protons. And I'm going to let you choose the correct answer or answers from the options. Another example. This one here is uranium 92, uranium 238, and we see that it is above 83. The other two examples, we had them sort of, under 83. So they were close close to the band, at least in terms of the atomic number. But uranium is all the way up there. So what does need to happen for uranium to get closer to the band? And we know that when radioactive isotopes decompose or when they decay, they may do it sequentially. They are transformed into different isotopes in a chain of reactions until they become stable. But what is the overall trend that needs to happen here? Well, we have a value for that ratio that is too high in protons and too high in neutrons. So we need both of them to go down. It would be like moving that red dot diagonally to the left so that it gets closer to the stability, to the band of stability. And having realized this, we can start thinking of the different types of radioactive decay. I'm gonna describe 4 or 5 different types, and do not memorize them. Just try to make sense of these decays, and then all you have to do is recall the logic. Okay, so for the first one, and there's something I forgot to mention, I'm gonna have to get out of here and then come back. There's something I forgot to mention here is that some books you will find that they call the original, the reacting nuclide, decaying nuclide, they call it the parent nuclide, and the product, the daughter nuclide. That's the way that some people call them. So what we have here is the alpha decay first. Here's the nuclear reaction. And we see that something happens to the atomic mass and atomic number. So the alpha decay would be the emission of an alpha particle, which we already defined as a helium-4 nucleus. And let's look at the following slide because it's a little bit larger. So let's say that, and actually that's the way it works, that we go in and we run this reaction. We start with uranium-238 and we realize we have our ways in chemistry to measure or determine the number of protons and number of electrons, number of protons and number of neutrons. And we realize that the product we get is thorium-234. So if we started with uranium-238 and we get thorium-234, that's an indication to us that what was emitted was an alpha particle. Why is that? Because we look at the changes in atomic mass and atomic number. We see that it went from 92, the atomic number, to 90. So this particle must have taken those 2 units in atomic mass. In atomic number, I'm sorry. Atomic mass, we see it went from 238 to 234. So this particle that was released, emitted, must have taken those 4 units in atomic mass. So we have 2 protons, 2 neutrons. That corresponds to a helium nucleus. And that is what we call an alpha particle. And again, if you use He, it may be a little bit easier, more immediate to see the chemical reaction. So here we have the overall change. Both the number of protons and number of neutrons go down. Okay, so in which direction is that nuclide moving on the plot to become more stable? So remember, P, number of protons and number of neutrons, are both going down for uranium-238. So let's go back to the plot. We've got it here. So if both of them are going down, it's moving diagonally to the left and getting closer to the band of stability. That's how we predict, how we can tell which type of decay will happen. That's alpha decay. One of the 4 that we're going to be discussing. We have beta decay or emission. In this case, an electron is released, is emitted, and we know that electrons have an atomic mass of 0, an atomic number of -1. So we can either use that or use the actinium to see what's happening. Because when we add all of the masses, atomic masses, across the nuclear reaction, they must be the same on the left that they are on the right. And the same for the atomic number. Atomic number, the sum of the atomic numbers on the left must be the same as the sum of the atomic numbers on the right. So we can answer this question, what happened? The change of how many units in atomic mass? It went from 228 to 228, 0. And how many units in atomic number? 88 to 89, -1. So what is the particle that was emitted? An electron or beta particle. Now, the big question is, how come we can change the atomic number without changing the atomic mass? That's interesting, and we will answer that question on the next video.